Hey guys, so in this video we're going to cover how to calculate the equilibrium constant for modified chemical reactions. The law of mass action expression describes the relationship between the chemical reaction and the equilibrium constant K. Therefore, if there is some sort of modification to the chemical reaction, the equilibrium constant must be appropriately modified to maintain this relationship. There are three rules that can be used in the modification of the equilibrium constant. The first rule is that if the chemical equation is reversed, the equilibrium constant must be inverted. For example, the equilibrium constant for the reaction shown is the products raised to the respective coefficients over the reactants raised to their respective coefficients. From here on out, this expression will be referred to as K forward. However, if the reaction is modified and is reversed, the reactant becomes the products and the products become the reactants. Therefore, K reverse should be expressed as the concentration of product A raised to its respective coefficient A times the concentration of product B raised to its coefficient B over the concentration of reactant C raised to its coefficient C times the concentration of reactant D raised to its coefficient D. Therefore, we can see that mathematically K reverse is equal to 1 over K forward. This process is known as inversion. The second rule is that if the chemical equation is multiplied by some coefficient, the equilibrium constant must be raised to that same factor. For example, if the given expression is multiplied by a factor of 2, then the equilibrium constant will be modified. All of the exponents in the equilibrium expression will then also be multiplied by a factor of 2. By rules of exponents, the common factor of all the exponents can be factored out as an exponent to the original equilibrium equation. Therefore, the equilibrium constant is simply raised to the same factor that the initial chemical reaction was multiplied by. Now, the third and final rule is that if you add two or more chemical equations to obtain a final equation, you must multiply the equilibrium constants of the corresponding reactions to get the final equilibrium constant. For example, if we're trying to determine the equilibrium constant for the general equation A plus B forms C and D with its respective coefficients, but we do not know the equilibrium concentrations of the reactants or products, it can be determined from the known equilibrium constants for two related reactions. So in this example, we know the values for K1 and K2. So we call the equilibrium constant that we are trying to determine the equilibrium constant for the goal chemical equation, which in this case is going to be termed K3. Recall that K3 should be equal to the expression shown above for the law of mass action of the goal chemical equation. We can see that if the two chemical equations are added together, the intermediate E cancels out and yields the goal equation. Now, by writing out the equilibrium expressions for reaction 1 and reaction 2 and then multiplying them together, we can again see that the intermediate E will be canceled out from the equation, therefore yielding the equilibrium constant for the third reaction, which is equivalent to the law of mass action expected. Now let's try a problem to illustrate how to apply those rules. So in this problem, it states to predict the equilibrium constant for the first reaction shown, given the equilibrium constants for the second and third reactions. So in this scenario, K1 is our goal equation, and we need to manipulate equations 2 and 3 in order to somehow add up to give us equation 1. If we take a close look at our goal equation, we see that we have two A's on the reactant side. And if we look at the other equations that we have to modify, we can see that equation 2 has an A as a reactant, however, it only has a coefficient of 1. Therefore, if we multiply equation 2 by a coefficient of 2, this is going to give us the correct number of A's that we need for our goal equation. Now remember that for the equilibrium constant, if we multiply by some coefficient to the chemical equation, we're actually going to raise the equilibrium constant to that same factor. Now again, taking a closer look at our goal equation, we see that we have 3 D's as products, where in our third equation that we can manipulate, we have 3 D's as the reactant. So if we reverse this chemical equation, then we're going to have the 3 D's as the product, which should match our goal equation. And remember that when we actually reverse a chemical equation, our equilibrium constant must be inverted. So just to verify that our chemical equations will add up to give us our goal equation, I'm going to rewrite the expression with each modification that was completed. So for equation 2, make sure that you're multiplying each reactant and product by a factor of 2. And equation 3 should simply be reversed. Now after rewriting these chemical equations, we can see that we have the intermediate B and the intermediate C, 2 moles on each side, and after crossing those out, we're left with 2A forming 3D. So now that we've verified that our modifications are correct, we need to actually calculate K1, so the equilibrium constant for that goal equation. And in order to do this, we're going to take the equilibrium constants after we manipulated them and multiply them together. Because remember that if you add chemical equations, you actually need to multiply the equilibrium constants of the corresponding reactions. So our manipulated equilibrium constant for K2 is 0.0334 squared, which gives us 1.11 times 10 to the negative third. And our manipulated equilibrium constant for the third equation is the inverse of 2.35, which gives us 0.426. So if we multiplied these two values together, we get that K1 is going to be equal to 4.75 times 10 to the negative fourth. So this is the equilibrium constant of our goal equation. So overall in this video, we learned 3 rules that can be used to modify chemical equations in order to determine the equilibrium constant.